Welcome to my channel, guys. So in previous video, the theory of the shear reinforcement, I make some mistakes to give the full information about shear reinforcement. But in this video, with the example, I will tell you and I will rectify that mistakes in I make in previous video. So this is the example: a RC beam of 230 mm wide. So this is the width of the beam, 230 mm, and this is the depth of the beam, 450 mm. So it is the overall depth of the beam, not the effective depth. So reinforced with the 3 bars of the 16 mm diameter, means this is the number of bars 3, and this is the diameter of the bar 16. This is the grade of the steel Fe415. So on the tension side of the effective cover of the 50 mm, this is the basically theoretical part, tension side, and cover of 50 mm. So this is the effective cover, not the overall. So not the clear cover. If they give a clear cover, then we in addition to that, we we take the half of the bar diameter, and this give a effective diameter to us. So here they give us to effective diameter of the 15 mm. So we subtract the clear cover, effective cover in the depth to mm, to get the value of the effective depth. And vertical shear reinforcement with the full tension. So here no bend bar is provided, and the ultimate shear force is the 18 kilonewton. So we require the values in newton, so we take it as a 18 into 10 raised to 3 newton. So this is the width of the beam, 230 mm from here. This is the overall depth denoted by capital D, and overall depth. So this is the effective depth, small d, d minus d dash. D dash means effective cover. We subtract the effective cover from overall depth to get the value of effective depth. This is the 400 mm. Here is the AS, means area of steel. Area of steel is the, they give us as a 3 bars of the 16 mm diameter. So 3 into pi by 4 into 16 square. So this is the pi by 4 into 16 square is the area of the bar. So this is value is 603.18 mm square. Grade of the steel is the FOY for 115 Newton per mm square. VU is the ultimate shear force, 18 into 10 raised to 3 Newton. So first our step is the nominal shear strength, tau V, denoted by tau V. So here we go with VU, means ultimate shear force, divided by breadth in width of the beam into depth of the beam. 18 into 10 raised to 3 is the shear force, ultimate shear force. This is the width of the beam, this is the depth of the beam. We got the tau V, means nominal shear reinforcement, nominal shear strength of 0.86 Newton per mm square. So permissible shear strength of the concrete is the, it is depend on basically PT, means percentage of steel in a tension, or percentage of steel in a concrete. PT is area of the steel into 100 divided by B, means width of the beam, depth of the beam. So here we got it the value of 0.65 from solve this. So in the IS code of the IS 456-2000, they give us page table number 19, 100 AS upon BD. This is the value. So our value is 0.65. This is the in between 0.50 and 0.75. Basically we grade of the concrete uses M20. So 0.15 basic value is for the grade of the concrete is 0.48, 0.75 grade of the concrete is used as a 0.65. So this I solve it in front of you. So 0.48 plus, basically if you practice it, then you can easily solve it. This is the easy way, I think. This is the value 0.58 0.528 Newton per mm square. This is the value of tau c. If they are not giving us the uh, if they are not giving us the grade of concrete, we assume as a M20 grade of concrete basically. So our third is the maximum maximum shear strength in concrete. Maximum shear strength in concrete. Maximum shear strength in the concrete. Basically for the tau c max is equals to 2.8 Newton per mm square. This is basically for the M20 grade of concrete. From here we got the value M20 grade of concrete, and here we tau c max 2.8 Newton per mm square. So here we go with our fourth step. We compare above equations. So the value of tau v nominal shear reinforcement is the 0.86. Tau c is equals to 0.528 Newton per mm square. And tau c max is equal to 2.8 Newton per mm square. So the equation we got is tau c max, it is greater than tau v and it is greater than tau c. So for this condition we provide a shear reinforcement. For this we provide shear reinforcement. In this case we provide the shear reinforcement, but if tau c is here and tau v is here, then we provide the minimum shear reinforcement. So our fifth step is the find required shear reinforcement. So our required shear reinforcement is the VUS is equals to VU minus VUC. So basically VUC means the shear force taken by the concrete. So our VU is the 80 into 10 raised to 3 minus our VUC means shear force taken by the concrete is 0.528 into B into D. So our B is 230 mm and D is 400 mm. So from here we got the value of D 18 into 10 raised to 3 minus 0.528 into 230 into 400. So 31.42 into 10 raised to 3. 31.42 into 10 raised to 3 Newton per mm square VUS. We need this value. So our sixth step is we provide two-legged 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 8 mm stirrups. So if you provide greater size of the stirrups, then we can't bend it. So 8 mm is basically the standard we can provide, 8 mm. So here we go from the IS code 456 2000 vertical stirrup. If you provide the vertical stirrups in page number 73, the VUS, so here we go, VUS is equal to 0.87 FY ASV into D divided by SV. This formula in from the IS code, VUS is equals to 0.87 FY into ASV into D divided by SV. So we know ASV is the basically area of vertical stirrups. Here we provided two-legged of the two-legged means this is basically two-legged. This is the two-legged. So I write it in separate corner. So 2 into pi by 4 into 8 square ASV, area of vertical stirrups. So 2 into pi by 4 into 8 square, 100.53 100.53 mm square. So 0.87 FY is grade of the steel is 415, ASV is 100.53 into D, depth of the beam 400. So basically we need the value of SV. So VUS is the 31.42 into 10 raised to 3. Basically from here we got the value of the spacing of the vertical stirrups. So here we go for the answer is 0.87415 into 100.53 into 400 divided by 3.31.42 into 10 raised to 3, 462.07 mm. SV is equal to 462.07 mm. This is the, we cannot provide it because we know the standards of the shear enforcement. So our first standard is SV is equal to 300 mm. The value of spacing does not exceed the value of the spacing does not exceed the above value. So SV is the 300 mm first condition. Second is the SV is equal to 0.75 D. So this is depth of the beam, 0.75 into 400 is equals to 0.75 into 400, 300. So these two values are same, mm, 300 mm, 300 mm. Our 4 is basically ASV divided by B into SV is equals to 0.4 upon 0.87 FY. Our ASV is the 100.53 divided by B means width of the beam 230 into SV. Generally we provide it 462 point, sorry, from here we got the value of SV. So here is the SV, 0.4 divided by 0.87, FY means 415. So SV is equals to 0.4 into 230, 0.4 into 230 divided by 0.87 into 415 into 153. So something is mistaken. 230b basically, right? Not. Here we go. So some mistake I had done it. 100.53 into 0.87 into 415 divided by 0.4 into 230 is equals to 394. So we provide the 8 mm dia 2 legged stirrups at 300 mm center to center distance. So basically the two-legged stirrups just like this. This is the above view or the top view. So we provide the 16 mm of 3 diameter, 3 they give us 3 numbers of 16 mm diameter. So this is 16 mm dia, 3 numbers. We provide the anchor bar of 12 mm, 2 numbers, and this is the shear reinforcement 8 mm 2 legged 300 mm center to center. This is 30 mm width of the beam, and this is the effective depth or overall depth 450 mm. Not the effective depth, it is the overall depth for 50 mm. Thank you friends. Here we go. 450 mm overall depth, 230 mm width. So anchor bar of 12 mm 2 numbers. They gave us 16 mm 3 numbers. We provide the stirrups of 8 mm 2 legged stirrups 300 mm center to center. Thank you.